All right, well, the purpose of this video is to go over the next major topic in Chapter 4, which deals with the very common concept called limiting reactant, theoretical yield, and percent yield. And so what we're going to do is explain what all these things mean and do several practice problems together so you have a good handle on it. All right, first thing to spend some time on is to make sure that folks understand what a limiting reactant is. So let me go ahead and stay on that for a few minutes here. So a limiting reactant is also known as the limiting reagent. These two words really mean the same thing. It's a little bit of a contextual thing. People will call something a limiting reactant from the point of view of the chemical equation. So basically, if you have a chemical equation, these would be your two reactants, these two. And of course, that would be your product like we talked about last time. You would call it a limiting reagent when you're actually in the lab doing the mixing of the nitrogen and the hydrogen. So reagent is more of like the practical term. That's what you're actually mixing together to produce something, whereas limiting reactant is more of like the theoretical term, the species on the left side of the arrow. But it's the same thing. So I don't want you to get tripped up by that. It really means the same thing. So with the limiting reactant, there's really 4 definitions that are actually relevant, believe it or not. It seems like overkill, but to be honest, to fully understand it, it's actually good to think about all of these things as being true about the limiting reactant. So let's kind of list out what a limiting reactant is. The limiting reactant is the reactant. Whoops. Let me write that. The limiting reactant is the reactant that runs out first. So it's the reactant that when you're doing an experiment, it's the one that gets consumed first, the one that gets turned over or turned into product first. So that's one way of looking at the limiting reactant. The second thing is when the limiting reactant runs out, and actually let's use the word is consumed. That just means it runs out. The reaction stops because you don't have one of the necessary reactants anymore, so therefore you don't have any more reaction happening. The third way of looking at the limiting reactant is the limiting reactant is the reactant that limits, and that's why it's called limiting, that limits the amount of product produced. Or let's just say product formed. And by the way, the amount of product formed is called the yield. That's the amount of product formed. Because when it is consumed and the reaction stops, you can't get any more product, so that's the one that really kind of will limit how much you're able to make. So these are all kind of, it's redundant definitions, but they all kind of are good ways of thinking about it. The last one I want you to consider almost like your favorite definition, because the last one is the one that's going to help you solve these problems at least the same way that I do them, because it's kind of how I approach solving limiting reactant problems. The limiting reactant is the one, or the reactant, that has the potential to make the least amount of product. And just underline the least amount of product, because that's really the key statement here. So let's go ahead and, with these 4 definitions, use a very practical example to make sure we can understand what limiting reactant is. And I'm actually going to even step away from a chemical reaction and just use something even more tangible. And that is the making of a peanut butter and jelly sandwich. So let's go ahead and just envision that you all have a loaf of bread. Call it, I don't know, 10 slices of bread. Let's say that you have an entire jar of peanut butter full. This is a whole jar of peanut butter. And let's say you have a spoonful of jelly. Okay, so obviously we're attempting to make peanut butter and jelly sandwiches. All right, so let's go ahead and ask you the question, just based on your instinct, which one is going to be the limiting reactant? Most people will be able to tell pretty quickly that the jelly is the limiting reactant, but let's step back and actually apply these 4 definitions and be sure, because this is where the 4 definitions kind of really help be concrete in your mind. So the limiting reactant is the reactant that runs out first. So in the process of making your peanut butter and jelly sandwiches, you are going to run out of jelly first, correct? Yes. Secondly, when the limiting reactant is consumed or all used, the reaction will stop. True. Once you use that spoonful of jelly to make a sandwich, your peanut butter and jelly sandwich making days are over. You can't make anymore. So consider this kind of like a chemical reaction, even though it's not. The limiting reactant is the reactant that limits the amount of product formed. So once again, the jelly will limit how many sandwiches you can make, right? And so that definition also works. Now here's the one I want you to really grasp here. The limiting reactant is also the one that has the potential itself to make the least amount of product. So let's think on this for a minute, because this is how we're really going to want to think about it. How many peanut butter and jelly sandwiches could a loaf of bread make, assuming that you had plenty of everybody else? Well, if I said 10 slices, you could make 5 sandwiches. Okay, so that could make 5. How many peanut butter and jelly sandwiches could an entire jar of peanut butter make, assuming you had enough of everybody else? Well, maybe even you could make, 10 to 20 sandwiches, a lot of sandwiches with this jar of peanut butter. How many sandwiches can you make with a spoonful of jelly? Well, one sandwich with this. So this one is the one that has the potential to make in itself, like the inherent potential to make the least amount of the product. That is actually how you want to think about limiting reactant, because that's how you're going to actually do your problem solving techniques. So keep this definition in your mind constantly. So let me go ahead and erase this here. The key here as I'm erasing is that when you are in a lab doing an experiment, or a chemist is doing some kind of a chemical reaction, they don't necessarily have perfect amounts of everything in the beaker. Back to this analogy here, if we're considering that a chemical reaction, you don't necessarily start with 2 slices of bread and a spoonful of peanut butter and a spoonful of jelly. You might have excess or extra stuff in the beaker of something. And actually that's incredibly common. Seldom do you have perfect amounts of everything. And there's reasons for that that actually are kind of interesting, but you have to wait for the second level of chem to really learn those. But you don't always have the exact perfect amounts that you need for the chemical reaction stoichiometrically. You might have extra of something in that beaker. And so it's important to find out what is your limiting reactant. That's kind of the context of why we care about that. So let's go ahead and let's pivot now to a real chemical reaction. So basically, let's consider this reaction. We've done this one several times, nitrogen plus, now let's read it like I taught you how to read it in the previous video. 1 mole of nitrogen reacts with 3 moles of hydrogen to produce 2 moles of ammonia. Okay, so let's go ahead and say that someone is running this reaction, and let's go ahead and kind of set up a little practice question here. 10.0 moles of N2 is reacted with 15.0 moles of H2. Okay, and let's ask the question, which one is the limiting reactant? Okay, so first of all, the limiting reactant has to be one of the reactants. So obviously it's going to be either N2 or H2. Okay, this is a product, so that can't be a limiting reactant. It's going to be one of them. Now, a lot of people will look at those numbers and they'll say, well, if you had 10 moles of N2 and 15 moles of H2, then it must be nitrogen because you have fewer of him. And that is the wrong way to think about it. It is not necessarily the one that has the smaller number because it depends on how much you need stoichiometrically for the reaction to occur, which is why what you really need in your toolbox is a technique to figure it out. So the first thing I want to just notice here is that these limiting reactant questions, you're going to be given starting amounts of both. And so the technique is for you guys, when you're asked to find a limiting reactant, is to, I call it like run 2 tests. You're going to kind of run 2 tests. And the goal of the test, and it's just a dimensional analysis, but the goal of the test is to figure out which one of these, okay, this is what you want to think about. Figure out which one of these, this is a light bulb, that's what I want you to think about. Which one makes the least product? Which one, or let's say can make the least amount of product? Because as you remember, that was our kind of our go-to definition for limiting reactant, the one that has the potential to make the least amount of product. So our 2 tests are going to look like this. First, we're going to find out how much product he can make. Secondly, so that will be done on line 1. Actually, let's go ahead and just do that. So we're going to start with the 10.0 moles of N2, and we're going to ask how much product can he make? Well, really, I want you to recognize that's a stoichiometry question because we have info about nitrogen and we're trying to figure out how much product he can make, which means we need a mole to mole ratio. And that's exactly what and actually we're ready for it right now because this started in moles. If I had started in grams, you would have had to convert to moles first, but this one started in moles. So for every 1 mole, and I'm just building this straight from the chemical equation, for every 1 mole of N2, I can make 2 moles of ammonia. And I don't even need a calculator. 10 times 2 is 20. So this one can make 20 moles of ammonia. And now I run my second test. So that I did the first guy. How much can this guy make? So these limiting reactant questions will have 2 lines as part of your problem-solving technique. For if I have 15 moles of hydrogen in my beaker, how much product can he make? Well, back to my mole ratios. For every 3 moles of hydrogen, I can make 2 moles of NH3. So it's just a separate kind of run through, a separate test to figure out how much of the ammonia he can make. So 15 times 2 is 30, divided by 3 is 10. So once you run these 2 tests, you can identify which one is the limiting reactant. The limiting reactant will be whichever one can make less. So you look at the 2 numbers and you look for the smaller number. This is the smaller number, which means this is the limiting reactant. And I literally do that every time I solve it. Once I figure out the numbers, I pick whichever one is the smaller number because that means he made less. And I go ahead and I label that guy the limiting reactant. He's the reactant that can make the least amount of product. But there's really 2 other things that you can label, and you should label right away, even in your own work. If he's the limiting reactant, what that means is that the other reactant you have an excess amount of. So this one is called, most people would just say it is in excess. You have an extra amount of it because if you're not limiting, then you're the excess reactant. Let's just kind of think about that for a minute here. Once the limiting reactant gets consumed, and remember our definitions, once he gets consumed, your reaction stops. You don't have any more reaction happening, which means you will have leftover nitrogen in that container, whatever the reaction vessel is. So you have extra, you have leftover of the excess reactant, and that's fine. No one really cares. A lot of experiments are set up that way to have excess reactant at the end. So the other thing though, which is possibly even more important, is that the amount of product, so this number here, the smaller number, the amount of product that is made from the limiting reactant gets a name as well. This is what we call the theoretical yield. I'm just going to write TY, but it's this word here. It's the theoretical yield. Now let's just give a definition of theoretical yield. Theoretical yield on I guess the quickest definition is this. It's the amount of product made by the limiting reactant. Okay. It's the amount of product that's made by the limiting reactant. But why is it called theoretical yield? Well, the idea here is this. In a perfect world with perfection in every way, if you did this reaction with these starting amounts, yes, you would get 10 moles of ammonia. But things get caught on a beaker or on a glass stirring rod, or that they get left over in a beaker, or they evaporate, or there's a spill, or you have some kind of miscalculation in your measurements or something. Life is not perfect. This is the number that theoretically, that it's the amount of product that theoretically you should get if life is perfect. That's what theoretical yield is. Now, usually, amount can be in either moles or grams, to be honest. Both of those are different ways of telling you how much you have. Moles is an accurate way of telling you how much you have, but so is grams. I will tell you that 9 times out of 10, maybe even 99 out of 100, a question wants that theoretical yield in grams, okay? So it would tell you, though, it would tell you. So if we want to know how many grams of ammonia are going to be produced, we would just have to take this one further step and do a mole to gram conversion using molar mass. So nitrogen is 14.01. We're going to add 3 hydrogens to get the molar mass of ammonia, and it is 17.034 grams per mole. And I can do that in my head because it's times 10. So that's 170.34 grams as an answer. And then let's just be perfect with sig figs. If this guy had 3 sig figs, then our final answer would only have 3. So we would report this as 170 grams. And actually, this is a good example of, because it doesn't bump up to 171, it's 170. But this is a good example of an ambiguous significant figure situation. Because you can see I have a trailing 0, but my number doesn't have a decimal point. What some people will teach is that you should just put a decimal point behind that 0. But really, your best friend is to just to stick it in scientific notation. Oh wait, I want 3 sig figs. To put it in scientific notation, which forces a decimal point into it. And that way you have no ambiguity about your sig figs. So 1.70 times 10 to the 10 to the second grams would be the right answer. That's the theoretical yield. That's how much you should get from this reaction. Now, what I want you to notice is that this here, this number is nothing. This number never actually got made. It's like the peanut butter and jelly sandwich. It's the 5, pretend sandwiches that the bread could have made. You didn't make it. You didn't have enough of the jelly. So this is a nothing. This is just a it's just a fake number. Okay, there's nothing to label with it. That is everything. That's your theoretical yield. Now, oftentimes there is a follow-up. So actually, I just erased which one is the limiting reactant. I'll tell you this. Usually that's a part A. Which one is the limiting reactant? A part B to a question would often be calculate the theoretical yield. Okay, that's oftentimes a part B, but frankly, it's really easy because if you do it the way that I'm doing for limiting reactant, you basically calculate the theoretical yield in your process anyways, so it's really simple. Part C oftentimes would look something like this. If 155 grams of ammonia were produced, calculate the percent yield. The percent yield. Okay, so the questions aren't always in this form, but a lot of times they are. So now what we're getting to is this last topic called percent yield. And like I said, these are all connected. It's kind of one big story. So that's why it's, you know, just one heading. Percent yield is a equation. And percent yield, it looks like this. AY over TY times 100. Okay, if you can just memorize that percent yield is AY over TY times 100. Well, we already know that TY is theoretical yield. What is AY? And this is just mine. This is not a famous thing, but AY is just my abbreviation for actual yield. AY stands for the actual yield. Now we talked about this concept of, in theory, you should get 170 grams. Okay, that would be the right amount of grams. But things happen. Like I said, things get stuck on a stirring rod, a beaker, or whatever. You don't ever get what you should get, okay, because of all these different reasons. How much you actually get, in this case, is 155 grams. Now, sometimes it will say the words, if 155 grams of ammonia were actually produced. That would be a gift, you know, if they tell you it, because then your mind is immediately going to recognize that that's the actual yield. But to be honest, even if it's not written, when someone is reporting in this type of question how much you got, that's called the actual yield. And so let's calculate the percent yield for our experiment here. Now, notice for the sig figs, we did round at this step here because I wanted to present the three sig figs as an answer. However, if you're going to use that number in a subsequent step, you want to go back to the unrounded number because otherwise you're kind of introducing rounding error in the middle of a problem, which is a no-no. So let's do actual yield over theoretical yield. So 155, and notice it's going to be 155 grams, okay, up here, but this also has a gram unit. So the gram units are going to cancel, and percent yield therefore is unitless. It's just a percentage. So 155, where is it? 155 actual yield divided by 170.34, and then make sure that you times it by 100. It should be a percentage. So I am getting for this answer here, the percent yield, I'm getting 90.99. And if you look back at the sig figs that went into my problem, this one had 3. This one really also kind of was limited by the 3 there. So the answer would be, let's see, 90.99%, but with only 3 sig figs. This guy's bumping him up to that, so it would be 91.0%. Would be the right answer. 91.0%. So it's a pretty good percent yield. That means you actually got about 90% of what you expected. The percent yield has to be between 0 and 100, okay? And it really can be anywhere. You can get 20% yield, you can get 99% yield. It can be anything, just depending on the efficiency of a reaction. That is how you do a limiting reactant theoretical yield and percent yield problem. So now let's just go ahead and do one practice problem just to make sure we're good on it. All right, so let me pull up a practice problem. Hold on one sec. Actually, I have some right here. Okay. Let's go ahead and do this problem here. We have a chemical reaction. I'm just going to write, consider this reaction. And it's given. Notice that if I don't write phase labels, then you don't need to know them either. It's one of those things, you don't just create phase labels. You only write them if you are told them, okay? And then also, when someone gives you a chemical reaction, unless they are telling you to balance it, chances are they're presenting you a balanced chemical equation. It's not really normal, apart from a balancing equation type question, for a person to present you an unbalanced equation. But it's good to check. So let's notice the 4 phosphoruses, the 12 chlorines, the 12 chlorines. By the way, P4, we didn't talk much about this, but this is just elemental phosphorus. It's not a compound, correct? There's only one type of atom in there, so that means it's an element. It's actually a polyatomic element. We learned the 7 diatomic elements. I didn't stress the polyatomic elements, but he happens to be one of them. But it doesn't really affect your question at all. So let's go ahead and ask a question. Let's go ahead and say that 45.2 grams of P4 reacts with 351.8 grams of chlorine. Period. 85.2 grams of, what would his name be? Phosphorus trichloride is obtained. We could say produced, we could say collected, we could say yielded, we could say formed, all saying the same thing. That's how much you got, which, by the way, I hope you recognize that is your actual yield. That's the amount that you actually produced. The question then says, identify the limiting reactant or reagent, really doesn't matter what they call it. Calculate the calculate the theoretical yield of the product, which is in this case PCl3, and calculate the percent yield. All right, so anytime that I am solving for a limiting reactant question, I just go straight to run 2 tests, figure out which one makes the least amount of product. So here's your 2 starting amounts. I've got 2 starting amounts. I've got the amount of P4 and I've got the amount of Cl2. So let's go ahead and run our 2 tests. 45.2 grams of P4. Now, I'm trying to figure out how much product he will make. That means it's a stoichiometry question. I have info about P4. I'm trying to figure out how much product he makes. The way that I do that is utilize a mole-to-mole ratio, stoichiometry. But I cannot do that yet because I'm not in moles. I need to convert this to moles. And so I therefore need to find out its molar mass. Phosphorus is 30.97, but there are 4 atoms in there. That would be 123.88 grams per mole. And I'm going to go ahead and write moles of what back in, because I'm about to do a mole-to-mole ratio, and I really need to see who I'm talking about here to focus. So for every 1 mole of P4, I will make 4 moles of PCl3. And since I'm going to need to get my theoretical yield in grams anyways, this should actually say calculate the theoretical yield. I should tell you in grams. Should make it clear. But I'm definitely going to need it in grams when I go to do the percent yield. Let me go ahead and just knock it out right now. Technically, you can just figure out the moles of each. Figure out the limiting reactant based on how many moles they'll make, and only convert the other one to grams to get theoretical yield. But I'll just knock it out of the park right now. So let me go ahead and do the molar mass of this. 30.97 plus 3 of the chlorines. 137.32 grams per mole. But I'll since I kind of know I just did PCl3, I'll just write moles. You can cheat a little bit. Nobody really cares about what you write as long as you don't mess it up, what the numbers really mean. So this is the grams of PCl3. Okay, let me just run this through my calculator. And I'm not going to worry about sig figs quite yet. Let me just keep some digits here. 200.42. All right. Let's check the other one. 351.8 grams of Cl2. Okay, got to put it in moles. So I need Cl2's molar mass, 70.9 grams per mole. Just reading it upside down, grams per mole. Mole ratio. For every 6 moles of Cl2, I will produce 4 moles of PCl4. And you're saying that sentence in your head as you're writing it down. Don't just think 4, 6. Think of it, it's a relationship. Notice the words that I use. For every 6 moles of Cl2, I'll make 4 moles of PCl3. And the molar mass is still 137.32, so I can just use that again. All right, let's see what happens here. So I just did 351.8 divided by 70.9. I pressed enter. Now I'm just going to do times 4 because that's on top. Pressed enter. Divided by 6 because that's on bottom. Press enter. Times 137.32. 454.25 grams. So now I have really answered 2 questions. I look at the 2 numbers. Whatever number is smaller, that tells me what my limiting reactant is. My limiting reactant must have been P4. That means I had an excess amount of Cl2. So that's the first question. P4 is my limiting reactant, or you could just say phosphorus, elemental phosphorus. The theoretical yield is this number, the amount that's made by the limiting reactant. To present it in the 3 sig figs that would be required, it's another one of these ambiguous ones because it's 200 grams. So you would, to be perfect, you would put that in scientific notation because that allows you to present your 3 sig figs without any ambiguity, that they're all significant. So, but it's the same thing. 2.00 times 10 to the second is 200. Okay, so that's my theoretical yield, and my percent yield will just be my actual yield divided by, so 85.2 divided by, and actually I'm going to use the unrounded number, 200.42 times 100. My percent yield, so my final answer here, would be 42.5%. And that's the percent yield of this reaction. So not quite as efficient as the other reaction that we did where we got 90% yield, but that is another limiting reactant question. So I just thought of one other type of issue that can come up, not issue, but question that can come up. So let me actually address it with one more practice problem, and maybe I'll stop just at the first step here, but just to address it. Let's go with this reaction here, Fe2O3 plus 3CO yields 2Fe plus 3CO2. All right, so let's go ahead and put a practice question down. It says 13.5 milligrams. Let's use the name, iron 3 oxide reacts with 1.50 grams of carbon monoxide. Um, 8.3 milligrams of CO2 or carbon dioxide is formed. Actually, let me use the word is collected. Let's have you calculate the, well, actually, let's have you, so part A, identify the LR, the limiting reactant, and part B, calculate the percent yield. Let's just do this one. And then we'll be done. So, a couple little things here. We once again have two starting amounts. I've got the amount of iron 3 oxide, that's this one. That's how much they have of this species in the reaction vessel. And I'm reacting it with this much of the second reactant. So, and I'm trying to figure out the limiting reactant. So the technique is always just the same. Run the two tests side by side, figure out which makes the least amount of product. The difference with this one, I want you to notice, is that we have two different products. Okay, so in the previous examples, I only had reactions that made one product. There's a million types of reactions. Sometimes it's two things forming one. Sometimes it's one thing forming three. Sometimes it's two things forming two. It doesn't, you know, there's all sorts of different combos. The key here is this. If you are only trying to figure out the limiting reactant, and that's your only goal, you can just pick either product and figure out which one makes, you know, you could just pick the iron, for instance. Figure out how much iron he makes. Figure out how much iron he makes, and then pick the less, and that's your limiting reactant. So you just don't switch halfway through your test. You know, just stay on the same product both times, so you can compare apples with apples. However, if there's a follow-up question, like in this point, we want the percent yield of obviously a CO2. This is our actual yield because this is how much we actually obtained. Then it would be wise to fixate on the product that the rest of the question is about, because then you can kind of have some numbers to work with, you know, for the other parts. So since the rest of the question is about CO2, that's the product that we're going to use for our tests, okay? So let's run our test. So we got 13.5 milligrams of, I'm not going to use the word, I'm going to go back to the chemical formula. Now, here's a milligram. When you have a milli, you got to get rid of it. There's 1,000 milligrams in a gram. Let's hit it with the molar mass of the iron 3 oxide. 55.85 is iron. There's two of them. And we're going to add 48 for the 3 oxygens because there's oxygen is 16. So I'm getting 159.7 grams per mole. And mole of what? Mole of Fe2O3. And like I said, when we're trying to figure out which product, let's fixate on the one that the rest of the question is about. So we're going to do a multimole ratio between him and him. So for every 1 mole of Fe2O3, I will make 3 moles of CO2. And why not just get the grams? Let's just get the grams. We need the molar mass of CO2, 12.01 plus 32, 44.01. So let's go ahead and get that number. So I'm not going to worry about sig figs yet. So that's what I got the number there. And now the other starting amount. 1.50 grams of carbon monoxide. This one is not in milligrams, so I don't need to do a metric conversion there. Carbon monoxide. 28.01 grams per mole of CO. Now I'm ready for my multimole ratio to figure out how much product he can make. So for every 3 moles of CO, I can make 3 moles of CO2. Kind of watching my units cancel. And the molar mass of CO2 is still 44.01 grams per mole. So the reason this dimensional analysis is a little shorter is because we didn't have a metric conversion, but no big deal. All right, let's see how much this one makes. So times 3 divided by 3 would just be a 1, so I'm not even going to put those in my calculator. But you could if you want. 2, oh my goodness, this is a big difference. 2.3568 grams of the CO2. So, by the way, there are other ways to solve limiting reactants. Some people will approach it from the point of view of not which one makes the least amount of product, but how much of one reactant do you need to form with the starting amount of the other, and then they'll check to see if it's above or below that number. All of that's fine. Any way that gets you the same answers is good with me. I personally like this technique because in doing this technique, you basically solve for the theoretical yield immediately, which is like almost always part B of the question. So I think it's a faster, kind of more direct technique. But you can do it any way you want if you have a different way that you find online, or actually the book may even teach an alternate method, but one method is all you need. So which one made the least amount of product or has the potential to make the least amount of product? Definitely this one. That's your limiting reactant, which means this guy is in excess. You have an excess amount in your beaker of carbon monoxide, which maybe you could have guessed. If you look at the starting masses, they were way different. But, you know, you can't take that too far because, the molar mass of each species and the stoichiometry of the species gets, tends to, will affect that as well. But anyhow, this technique is the technique that you'll never make a mistake with. So that's your limiting reactant, which means this is your theoretical yield. If we want to report it with 3 sig figs, we would just say 0.0112 grams of CO2. Because these are leading zeros, they are not significant, and those are your 3 sig figs. That 6 will bump him up to a 2. And then our percent yield, 8.3 milligrams. Okay, this is good. Let me get some room here. Percent yield is actual yield over theoretical yield times 100. So if I'm always very cognizant of units, and you need to be, because never strip him of him, because you might make a terrible mistake. So it's 8.3 milligrams, correct? If you put in your theoretical yield, we have it calculated in grams. And hopefully you'll see that that's not going to work, because unless those units cancel, they are alive and they will come into your answer, and there is no unit in a percent yield. So they've got to cancel. So you have two choices. You're going to put him in grams, or you're going to put him in milligrams. And honestly, you can do whatever you please. I will go ahead and convert him to milligrams. Okay, now you can do it just as a dimensional analysis. Just write this number first, okay, and then do, for every 1 gram, there's 1,000 milligrams. So you're timesing by 1,000 to get milligrams. If you are to the point that you can see that, that this many grams would be 11.2 milligrams. Of course, yeah, 11.2 milligrams. That is also fine, as long as you get 11.2 milligrams reliably. That will now cancel, and by the way, that the actual yield has to be smaller than the theoretical yield too. So if the actual yield is bigger, you have a mistake. The actual yield, you have to have less made than you would expect. It's just, that's the only way it goes. So 8.3 divided by 11.2 times 100, and I'm getting 74.1%. Actually, this one here only has 2 sig figs, so that will limit this answer to 2 sig figs. So the perfect answer is just 74%. So that question allowed us to deal with a couple more little intricacies that could show up on these type of questions. But that's how you do limiting reactant, percent yield, theoretical yield questions. We did not do any types of questions that ask you to calculate the amount of excess product at the end of the reaction. There are some of those in the book. Essentially, all you're going to be doing is, if you end up being presented with one of those types of problems, is use stoichiometry. The limiting reactant will dictate everything. So use stoichiometry with the limiting reactant to figure out how much of the other product will react. Okay, so just use stoichiometry to figure out the amount of the other reactant that will react. And then all you would do for those is subtract that amount from your starting amount, and that would be the leftover excess reactant. But I don't stress those types of questions because I don't actually push those on my test. So this is the type of question that you're more likely to see. Okay, so thank you for your attention. That was really, really good, and have a good rest of your day.